Hi guys, Miss Barber here. We are now on to section 1.8. It is titled Continuity. Let's begin with the definition. We say a function f is continuous at a, an element of the reals, if and only if the limit as x approaches a of f of x equals f of a. This is actually three requirements. The first is that the function evaluated at a must be defined. The second, the limit as x approaches a of f of x exists. And third, the limit as x approaches a of f of x equals f of a. That is, the limit and the function must both exist. Let's look at criteria number 2. And that is the limit as x approaches a of f of x exists. This means, so let's go ahead and do the double-sided arrow, which is if and only if the limit as x approaches a from the left of f of x is the same as the limit as x approaches a from the right of f of x. That is, the limit exists only when the left hand and the right hand limits are equal. And we follow by saying if any of the above fails, that the function is discontinuous at a, and we say f has a discontinuity at a. Example, the graph of the function f of x is given below. Determine intervals of continuity. Now, for the solution, let's look at this graph and observe that it's got three separate chunks and a dot. We can visually detect three different areas of discontinuity. What we want to do is make sure that we can make it fit our definition of continuity. So let's begin by looking at x equals -3. Now, if you were to look at the value of the function, it exists. Not concerned what it's equal to. Now, the issue though is if we look at the limit as x approaches -3 of f of x, we notice that it does not, because the left-hand limit and the right-hand limit are not the same, even though they each exist. So we know that because it doesn't meet the definition of continuity, which also coincides with what we visually see, we see that the function is discontinuous at x equals -3. Now, the next x value of interest will be at x equals -1. Let's observe that it's standard and customary to use a dashed line, and if it's vertical, it typically indicates a vertical asymptote. Vertical asymptotes are where the function doesn't exist at all. That would be the x value that makes the denominator 0. And so we start with the function evaluated at -1 is undefined. And since all three parts have to be satisfied, the fact that the first one is not satisfied tells us the function is discontinuous at -1 as well. And finally, let's see how the graph of this function fits in with our definition of continuity at x equals 2. If we evaluate the function at f of 2, we notice that you have a solid dot that's equal to 1, so the function exists. Let's compute the limit. We want the limit as x approaches 2 of f of x. We note that as you get closer and closer to 2, the function from the left-hand side and the function from the right-hand side, the graph of it approaches -0.5. So the first two parts of the definition of continuity are satisfied. That is, the function exists and the limit exists. However, the function value f of 2 equals -1, which is not the same thing as the limit as x approaches 2 of f of x. So it does not satisfy the third part of the definition of continuity. So we are able to now say that the function is also discontinuous at x equals 2. Let's practice writing the intervals of continuity. We begin by looking at from the left to the right, from negative infinity to where you have the open hole at -3, so we'll use an open parenthesis. So up to -3, but not including it. If you were to put your pin on any part of that graph, you can move up or down without having to lift it. It satisfies the parts of the definition of continuity, so we'll do that. Union. Now the next piece, we actually get to include the -3, so I'm using a bracket. And the graph continues indefinitely to -1, but it never actually reaches it, so you use a parentheses. The graph of the function resumes again at -1, sort of, and it is smooth, continuous until you get to 2, but 2 is not included, so we'll use the open parentheses. And the last piece, we start at 2 and go to infinity. As a quick reminder, brackets mean the endpoint is included, and the parentheses means that the endpoint is not included. There are 3 types of discontinuities. The first one I want to talk about is a jump discontinuity. In the previous exercise, we have a jump discontinuity at x equals -3. You have a jump discontinuity when the limit as x approaches that x value from the left of the function and the limit as x approaches that value, which is -3, from the right of the function, do not equal each other. You can see the jump in the graph. This gives you the continuity definition of why it is a discontinuity. It is jump because the left and right hand limits do not equal each other. We also have an infinite discontinuity, and that happens at x equals -1. Couple of things to keep in mind. When you have an infinite discontinuity, the function at that place typically is undefined or does not exist, and the limit as x approaches that x value typically goes to either infinity or -infinity, hence infinite discontinuity. And finally, let's look for a removable discontinuity. This is often called point discontinuity as well, and we have a point or removable discontinuity at x equals 2. This typically happens when you get a function value, so the function evaluated at 2 is -1, and you actually have a defined limit. So we have the limit as x approaches 2 of f of x equals -0.5. When the existing limit and the defined function values do not equal each other, we have a removable discontinuity. So the first was satisfied, the second was satisfied. However, the function evaluated at -2 is not the same value as what the function approaches when x approaches -2. This is where you get the removable discontinuity. Continuity of some types of functions. 1. Polynomials. Polynomials are continuous at all points of a that's an element of the reals. That's because the limit as x approaches a of the polynomial is always equal to the polynomial evaluated at a. Rational functions, that's 2, are continuous at all points for which the denominator does not equal 0 And finally, 3, trig functions. Sine and cosine, those are nice waves. They're continuous at all a. Now, the tan, secant, cotangent, and cosecant are continuous at all a in their respective domains. Generally, if f and g are continuous at a, then so are the sum of the two continuous functions, the product of two continuous functions, a constant times a continuous function. F over g is continuous as long as g at a is not equal to 0. A function raised to a positive integer is continuous, and a function raised to a rational power where m and n, that's m over n, are both integers, and if the function is equal to or greater than 0 for when you're taking an even root. Definitions. We say f is right continuous at a if and only if the limit as x approaches a from the right of f of x equals the function evaluated at a. Graphically, that would look like, let's find an a, solid, and then you have a graph continuing to the right. Similarly, f is left continuous at a if and only if the limit as x approaches a from the left of f of x equals f of a. Note that f is continuous at a if and only if the function is both left and right continuous at a. And for an interval I, we say f is continuous on I if and only if f is continuous on each point of I. When I includes left or right respectively endpoint, we mean that the left or respectively right endpoint is continuous at the left or respectively right endpoint. Continuity exercises. Example. Determine the value or values for which f of x equals the rational function x squared minus 4x plus 3 divided by x squared minus 9 is continuous. We know that f of x, the function, is undefined where the denominator equals 0. So we want to solve for where x squared minus 9 equals 0. We can factor the difference of squares, x squared minus 9, as x minus 3 times x plus 3. And solving for the x's, we get that f is undefined, therefore discontinuous, spell that correctly, at x equals 3 and at x equals minus 3. The problem said determine the values for which f is continuous, not where it may be discontinuous. So let's answer. We'll say f is continuous on from negative infinity to negative 3, not including negative 3, union negative 3 to positive 3, neither of the endpoints included, union 3 to positive infinity. Let's classify what types of discontinuity we have at negative 3 and at 3. To do that, we need to find the limit. So to classify, let's begin by computing the limit as x approaches 3 of our rational function x squared minus 4x plus 3 divided by x squared minus 9. When you evaluate, that is, just do the direct substitution, you're going to have 3 squared minus 4 times 3 plus 3 in the numerator, divided by 3 squared minus 9 in the denominator, which gives you 0 over 0. This means we have something that is indeterminate, and we need to do something else, typically factor and simplify. So let's see what happens if we take the limit as x goes to 3, and in the numerator we'll factor the x squared minus 4x plus 3, so that'll be x minus 3 times x minus 1, divided by, in the denominator, we factor the x squared minus 9. That's a difference of squares, so you get x minus 3 times x plus 3. The x minus 3 in the numerator and the x minus 3 in the denominator are common, so we can cancel those. This will be the same as the limit as x approaches 3 of x minus 1 divided by x plus 3. Let's do direct substitution again. Putting in 3 in the numerator, 3 minus 1 is 2. Putting in 3 in the x for the denominator, 3 plus 3 is 6. And that reduces to 1/3. So when we simplified it, the limit actually went to a value. Then we can say, thus, x equals 3 is a removable discontinuity and x equals negative 3 is a vertical asymptote. And where you get the vertical asymptote, you have an infinite discontinuity. Determine the value or values for which g of t equals t minus 1 divided by the quantity 1 minus cosine 2t is continuous. G of t is discontinuous where the denominator 1 minus cosine of 2t equals 0. Those specific t values will give us the vertical asymptotes. Let's solve the trig equation 1 minus cosine 2t equals 0. To solve that, let's isolate the cosine 2t, and that would equal 1. The question to answer here is, what values of cosine equals 1? Well, we know it happens at 0, at 2 pi, at 4 pi. So it appears that when 2t is equal to multiples of 2 pi, let's go ahead and divide the common factor of 2. So we got t equals, the 2's are canceled, so 2 pi. And of course, n is an element of this capital Z stands for integers. This tells us if you take the limit as t approaches an integer multiple of pi of g of t, that'll get us to either plus or minus infinity definition of vertical asymptote. Then we can conclude the function g is continuous everywhere except where t equals 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, dot, dot, dot. You get the picture. We can write this in compressed form as t equals n times pi, where n is an element of the integers. Example. Determine whether f of x equals x plus 2 for x less than 3, 12 minus 2x for x equal to or greater than 3 is continuous at 3. Recall, continuity is a three-part definition. 1. Does the function exist at 3? 2. Does the limit exist at 3? And finally, the third part is the function value at 3 and the limiting value as x approaches 3 the same. So with that in mind, let's begin with the first part. Is f defined at 3? Let's compute. F of 3, the equal to or greater than tells us 3 is included in the second line, so we compute this at 12 minus 2 times where the x was, we put in 3. 2 times 3 is 6, so 12 minus 6 is 6. Yes, the function is defined at 3. Next question. Does the limit as x approaches 3 of f of x exist? To answer this, we need to compute both the left hand and the right hand limit. So let's start. The limit as x approaches 3 from the left of f of x. Left means less than, so we're going to compute that for the x plus 2. So that would be the limit as x approaches 3 from the left of x plus 2. Doing direct substitution, you're going to get 3 plus 2, which is 5. So the left-hand limit exists. How about the limit as x approaches 3 from the right of f of x? From the right means from numbers bigger than 3, so we want x to be equal to or greater than 3. So we're now going to compute the limit as x approaches 3 from the right of the 12 minus 2x piece, which we previously computed as 6. Let's observe that the limit as x approaches 3 from the left of f of x is not the same as the limit as x approaches 3 from the right of f of x. So, to the question, does the limit of f of x exist? The answer is no. And if any of the three parts fail, the function is not continuous at that point. So, is f of x continuous at 3? No. F of x is not continuous at x equals 3. Theorems on composite functions. First theorem. If g is continuous at a and f is continuous at g of a, then f composed with g is continuous at a. Just a quick notation reminder on how to work with a composition of a function. F circle g is read f composed with g of a is the f of g of a. Composite functions, you work from the inside out. And the next theorem, if the limit as x approaches a of g of x equals L is continuous at L, then the limit as x approaches a of f of g of x equals f of L. Let's work with that just a little bit. The limit as x approaches a of f g of x is the function evaluated at the limit as x approaches a of g of x. And if that inside function. We work from the inside out. The limit as x approaches a of g of x equals L, then f is evaluated at L. Example, evaluate the limit as x approaches 0 of pi times the cosine of the tangent theta. Let's observe that cosine of tangent theta is a composite function. So we'll use the theorem we previously looked at and say that the limit as theta approaches 0 of pi times the cosine of the tangent of theta is equal to, we can put the pi times the cosine outside of the limit as theta goes to 0 of tangent of theta. Continuing, you'll have pi times the cosine of, and if tangent goes to 0, you may want to do a little think back on the trig. Remember, tangent theta is sine theta over cosine theta. And if we were to evaluate, say, at 0, then the tangent of 0 is the sine of 0 over the cosine of 0. 0 over 1 is just 0. For the limit as theta approaches 0 of tan theta, we put in 0. And now we're going to have pi times the cosine of 0 is 1. So, pi times 1 is pi, and we have that the limit as theta approaches 0 of pi times the cosine evaluated at the tangent of theta is equal to pi. The intermediate value theorem. Suppose f is continuous on the closed interval from a to b. If m is a number between f of a and f of b, then f of c equals that m for some c that's between a and b. What does that look like? Let's draw a plane. We'll label x and y. I'll assign a point A on the negative x-axis and B on the positive x-axis. Let's assign A evaluated at F in the third quadrant and B evaluated at F in the first quadrant. The instruction says F is continuous. So let's draw a continuous function that's continuous between A and B. If M is a number between f of A and f of B, then M occurs somewhere along the curve between A and B. We'll call that M. What we are told here then is that there exists some C that is between A and B, as illustrated here, that when C is evaluated in the function, you get exactly the M value. Example, show that x to the fifth minus 3x squared plus 2x plus 5 equals 12 has a real solution. Let's see if we can use the intermediate value theorem. First, let's go ahead and identify f of x to be the function x to the fifth minus 3x squared plus 2x plus 5. That's a polynomial, so we know that f is continuous everywhere, but we also need it to be continuous on a closed interval. So let's see pick some arbitrary numbers. I want to pick 1. So one endpoint would be 1. An f of 1 would be 1 to the 5th minus 3 times 1 squared plus 2 times 1 plus 5. And when you compute that, you're going to have 1 minus 3 plus 2 plus 5, which is 5. I need a right endpoint, and for this, I'll pick the number 2. We know that f is continuous on the closed interval from 1 to 2, but let's compute the function value. That would be 2 to the 5th minus 3 times 2 squared plus 2 times 2 plus 5 is 29. The intermediate value theorem tells us that since 12 is between 5 and 29, by the intermediate value theorem, there exists a C that's between our endpoints 1 and 2, so that the f evaluated at that number is 12.